So I'm going to talk about an old problem, and that's melodic similarity. It's an interesting problem because it's one that's been approached both from a psychological perspective and a computational perspective. So it seems like a natural fit for this CogMIR. So ways of looking at this psychologically or empirically at least, are as follows. We can have people listen to 3 melodies and choose which 2 are the most similar. We can have a common referent and everyone judges how much each melody resembles the referent, or we can have 2 side-by-side comparisons and people, on a Likert scale, judge how similar these things are. Computational approaches is a host of things, from edit distance measures, hidden Markov models, geometric approaches, n-gram approaches. Psychological meets computational. So our thinking was that this could be approached from the bottom up. By doing so, we have a kind of a toy model, to use the word that's been used before. It wouldn't be robust, but it would have some generalizability, and maybe we could build on it. And we thought that we could do this using multiple linear regression. So let's manipulate one variable at a time and see how much impact this has on similarity ratings. So we started with variables that have some cachet, if you like, within the music cognition community. They seem to support representations of music. And so we manipulated pitch distance, pitch direction, metric salience, melodic contour, and tonal stability. And by manipulate, what I mean is we had standard melodies, and we would manipulate tones within that standard according to these parameters. And as a listener, you were to judge how similar the standard melody and the comparison melody was. And then we track the impact of that change using multiple linear regression. So 3 experiments that I'll talk about in the next 2 minutes are to manipulate one note at a time. Then what we did is, so that's a start. Let's manipulate all these variables one note at a time. Then let's look at where the change happens across the melody. Is the change more impactful at the very beginning of the melody? Probably. At the very end of the melody? Probably again. And then finally, how can we scale this? How can we look at multiple note changes within a melody? And that's what we've tried to do. So step 1, we're manipulating in an 8-note sequence, note 4 or note 5, so a weak or a strong metric position in a 4/4 framework, and we manipulate according to those parameters. What we found using multiple linear regression is that when our comparison melodies are not modulated in key, it's the same melody except for a 1-note change, pitch distance, pitch direction, and melodic contour are contributing to explained variance. When we transpose the comparison melody, so it's no longer in the same key, then melodic contour is still a predictor, but now we've got tonal stability. And my interpretation, or our interpretation of that, is that once you introduce this transposition and the listener is trying to judge melodic similarity, they're searching for deeper structures. Tonal stability emerges as something important, whereas it wasn't previously. Step 2, as I said, we're manipulating the position within which the change takes place. We looked at different functions, so a combined linear function, a couple of quadratic functions, and what we were trying to do is create weightings for the position of change, and then evaluate the contribution of primacy and recency. What we find is that when we don't transpose our comparison melody, then introducing these 3 here, these 3 columns here, include the primacy recency functions. These are the two quadratic quantifications, and that's the linear quantification. So there's an improvement in explained variance when we introduce that primacy-recency function for non-transposed melodies. There's no improvement, a decline it seems, which is hard to explain when we have transposed comparisons. The final step of modeling from the bottom up that we did here was to look at multiple note changes. So can we take the linear regression solution for each, let's say there's 5 notes changed in an 8-note sequence. Can we take the linear regression solution for each of those, average across those, and again we're using the weighting functions for position in order to come up with a model of melodic similarity. So the details of this are forthcoming in that journal, and I'll say that we did pick an easy target, a Mongo-Sankoff model, string matching edit distance measure, and we found that this approach outperformed that particular approach. That's my talk, possibly 5 minutes. And yes.
But over 70% of the variance is not explained by the independent variables.
In those initial models, that's correct. Yeah.
Right.
So there's a lot.
Thoughts about that?
That our manipulations affected other factors that we are not accounting for. So although it seems like a good place to start, manipulate one thing at a time, I think we're introducing change on other parameters that we're not quantifying, that are not in our model. Yeah.
Was there a lot of variance between subjects in terms of how they responded to the manipulations? Was it all over the map?
No, I wouldn't say so. I don't think that's the problem.
Oh.
Yeah. Okay. I have the benefit of pulling the plug on myself, and